Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I'm pleased to present our next speaker, Professor Carl Rubin of UC Irvine, who will talk to us about Selmer ranks of elliptic curves and families of quadratic twists.
Thanks very much, and thanks for the invitation to speak, especially because I'm not really saying anything about elliptic curve computation, although it certainly will be about elliptic curves, and it's not really a stretch to say it's about elliptic curve calculations. So everything I'm going to say today that's new is joint work with Barry Mazur. And it's ongoing in the sense that we can't, as you'll see, do everything we would like to do, but still have some ideas to try. So I want to talk about the following situation. I'm going to fix a number field K. So just some finite extension of the rational numbers. E will be an elliptic curve defined over K. And the basic question, which I'd like to be able to talk about, is how does the rank of E vary as E varies over K with K fixed? So how does the rank of the group of K rational points vary as E varies, but with K fixed? And that's kind of vague. How is E varying? But it should have a nice answer that really doesn't depend on how E varies, as long as it's varying in some reasonable way. So, and since I can't really answer it, I don't have to specify. Okay, well, first of all, it's too hard to prove a lot in this situation. And so what do you do when you want to talk about ranks of elliptic curves and it's too hard? You look at the Selmer group instead. So let me talk about that for a bit. So look at the 2 Selmer group. This is, after all, what you would do if you wanted to compute the rank. And it's just much easier. So I'll define the Selmer group a little bit later. But for now, let me just put it into its natural context. Namely, the Selmer group lives in an exact sequence. We have our Mordell-Weil group, K rational points, modulo 2, sitting inside the 2 Selmer group of E over K. So when you do a 2 descent, compute the 2 Selmer group, you're bounding the rank because this group is contained in this group. The error term is, and we'll just take this as the definition of the Shafarevich-Tate group, or the 2 torsion in the Shafarevich-Tate group. That's the error term. So again, I'll define the 2 Selmer group later, but for now, let's just think of it as an upper bound for the Mordell-Weil group modulo 2 in this sense. So these are all vector spaces over the field with 2 elements. And so what we can take away from this exact sequence is that the F2 dimension of the Selmer group, well, it's the sum of the dimensions of the outer 2 terms. What's the F2 dimension of this? Well, it's essentially the rank of E, except if E of K has 2 torsion, then that contributes to this dimension also. So the dimension of this term is the rank plus the F2 dimension of the K rational 2 torsion. So that's the first term. And then plus the F2 dimension of the Shafarevich-Tate group, the 2 torsion. And as I said, this is an error term that we won't be able to say too much about. But if we want to bound the rank, here certainly we have an upper bound for the rank. But to make the later comments come out simpler, I want to look instead of just this dimension, I want to take this dimension and subtract the dimension of the 2 torsion from it. And so I'll define that. I'll just define S of E over K to be this modified 2 Selmer rank. So the dimension of the 2 Selmer group minus the dimension of the 2 torsion.
You're at S of E over K.
E over K, thanks. I mean, mostly K is going to be fixed, but I'm going to keep it in the notation anyway. Okay, and so now we can ask questions about the sizes of the Selmer group or about this rank. So what can we say? Well, first of all, just looking at this formula, we see that the rank is bounded above by the Selmer rank. And second, well, if the Shafarevich-Tate group is finite as conjectured, then this dimension is even. So that's a classical fact. If the 2 part is finite, this dimension's even. If the 2 part's infinite, this might still be even. But let me just conjecture for now that this dimension is even. And that gives us a congruence then, which is that the rank of E of K is congruent to this Selmer rank mod 2 conjecturally. And so the way we're going to use the Selmer rank to deduce something about the rank is just the easy consequence, namely if the Selmer rank is 0, well, the rank is 0. If the Selmer rank is 1, well, from here, all we know for certain is that the rank is either 0 or 1. But if we accept this congruence, then it's either 0 or 1, but it's odd. So then, again, under standard conjectures, the rank is 1. And if the Selmer rank is bigger, well, we don't know a whole lot, except maybe the parity of the rank. Okay, so we can ask the same kind of question here. How does the Selmer rank vary as the curve varies? Okay, that turns out to be much more tractable. So first of all, I guess I should have said back here that there's a sort of folklore conjecture that 50% of elliptic curves over K have rank 0, and 50% have rank 1. And 0%, although not 0 curves, have rank greater than 1. So this conjecture has been around at least most of my adult life, except for maybe a brief period in the 1980s when people were sort of confused and weren't sure, but people seem to believe now. The Selmer rank is different, as we'll see in a minute, but let me state a few theorems. So the first one is a recent theorem of Bhargava and Shankar. And what they proved is that the average So this is with k equals q. The average value of the order of the two Selmer group as E varies through elliptic curves over Q. And average, now we're counting them by the height of the elliptic curve, just the heights of the coordinates of the Weierstrass equation. And they proved the amusing result that this the average value of the sizes of these F2 vector spaces is 3. Which, anyway, I think is amusing. As a corollary of this, I mean, if we know that the Selmer groups on average aren't too big, that's telling us that the ranks aren't too big. And if you think about it for a while, the worst case is when half of these Selmer groups have order 2 and half have order 4. And that's the case, would be the case if half of the ranks were 1 and half of the ranks were 2, and there were no Schaffer-Rayleigh-Tate groups floating around. So what you can deduce from this is that the average of the rank as E varies is at most 3/2. And in fact, they have some stronger results using the 3 Selmer group instead of the 2 Selmer group. I think they now they prove that this average is less than or equal to 7/6 or something like that. Which is not 1/2, but it's certainly progress. And you can deduce from this that some positive proportion of elliptic curves have rank 0. So I don't have any good methods for studying all Selmer groups the way they did. And so instead, I want to restrict to special families. And those are the families of quadratic twists that were in the title of my talk. So let me say what I mean by quadratic twists. So I have my elliptic curve over some number field k given by an equation y² equals f of x with a cubic polynomial f. And if f over k is a quadratic extension, then by E upper f, the twist by this quadratic extension, I just mean, well, it's easiest to write it delta y² equals f of x, which you can put in a Weierstrass form if you want, where f is k adjoin square root of delta. And I might call this E upper delta sometimes, but I really want to emphasize that these twists correspond to the different quadratic extensions of k. And so I want to count curves in this family. So how are we going to do that? Let me write n sub r of Ex. This is going to be the number of quadratic extensions f over k such that the Selmer rank of the twist E upper f is r and well, we just have to bound our set of f somehow, and I'll just say that the absolute discriminant f over q is less than x. Okay, so as x varies, we're counting the number of twists with Selmer rank r, and q sub r of x is just going to be the number, the total number of quadratic twists. In that range. Okay. And so then there's a theorem due in different pieces to Heath-Brown, Swinnerton-Dyer, and Kane. And they proved that, so this is again, so K is Q. And so if all the 2 torsion is rational, so if the 2 torsion is contained in E of Q, then you can compute they compute the density of twists with Selmer rank R, namely the limit x goes to infinity, the number of twists up to x with rank Selmer rank R divided by the total number of twists up to x is given by a constant C sub r, which I can tell you. C sub r is product n equals 1 to infinity. 1 plus 2 to the minus n inverse times 2 to the r minus 1 divided by product n equals 1 to r 2 to the n minus 1. It doesn't matter exactly what it is. It matters that they can tell us what it is.
It's just Q of x, right?
Sorry. Yes, Q of x. Thanks. Okay, and so one thing you can deduce from this is that the average, so corollary, the average of the sizes of the 2 Selmer group of EF in this family. Now, all of the if E has all its 2 torsion rational, so does every quadratic twist of E. You can see that from the formula, and we'll see it again later. So all of these curves, the Selmer group already has 4 elements just coming from the torsion. And so I really want to take this and divide it by 4. But this average is 3. It's the same that Bhargava and Shankar got. And the other slightly, not curious, but surprising thing is that if we take the average not over all the curves in this family, but just the ones with even Selmer rank, we also get 3. Or just the ones with odd Selmer rank, we also get 3. So the average over F with S, E upper F over Q even is 3, and the average odd is 3. So somehow the even ones and odd ones are going on independently with this same average. So what do we expect? Well, it doesn't take too much generalizing of sort of this result and some of the things I'm going to say in a little bit to say that, well, more or less that the same thing should happen for any k and any E over k. So E over k. Just any elliptic curve now. What I really want to say is that one of the following three things happens. So one of the following happens. The first is exactly this, that the limit, so first limit x goes to infinity, the number of twists with rank, Selma rank R, is C sub R with the same C sub R, and this is for all R. Second, this same limit has two possibilities, namely it's twice C sub R if R is even, and 0 if R is odd. And third, the reverse. It's 0 if R is even, and twice C sub R if R is odd. We can say a little bit more, and that is that cases 2 and 3 happen if and only if K is totally, the number field K is totally imaginary, so no real embeddings. And the elliptic curve E that you start with gets good reduction everywhere over some abelian extension of K. So the exact condition is not important. It's just meant that to show you that these are very special. And the logic is that in this special situation, root number calculations tell you to expect that the Selma rank is either even, that the parity doesn't change when you do a quadratic twist. So if you start out with something with even Selma rank, every quadratic twist will have even Selma rank. Or if you start with odd Selma rank, every quadratic twist will have odd Selma rank. But of course, over Q, we're never in this situation. Totally imaginary means your field has no real embeddings. So we're just in case 1. Okay, so what can we prove in general? So this, as I'm going to state it, is due to Mazur and myself. But in the special case, which I'll describe in a second, it's due to Ono and Skinner. So that's when K is Q and R is 0. I'm not going to state the most general theorem just to make life simpler. Let me suppose that K has a real embedding. So in particular, it's not totally imaginary, and we're not going to be in, we don't expect to be in these cases. Let me get this right. So this condition is not important, but this one is. So also suppose that E of K has no two torsion, no K rational two torsion. So it's just the opposite of the case that these people considered. And the idea is if you're doing a sort of classical two descent, it helps a lot to have rational two torsion. But the approach the method we're going to be using is quite different, and it turns out to work much better when there's no two torsion. Then for every r less than or equal to the rank of the curve you start with, or r equals 1 if the curve you started with happened to have rank 0, n sub r, the number of twists of Selmer rank equal to r, is at least a constant times log x, x over log x. X over log x to the 2/3. So not positive density. I should say that this q of x grows like a constant times x. So this is less than saying a positive proportion have rank r, but at least it is infinite. And so if in addition the discriminant of E is less than 0, and now what I mean is we have at least one real embedding of k. If the discriminant under that embedding gives you a negative real number, then in fact this holds for all r. Then for all r, n sub r dx greater than greater than. In fact, it holds with a better constant. X over log x to the 1/3. Okay, and let me just mention a corollary of this result. It's not quite a corollary of this result. It's a corollary of the stronger result I didn't quite state, but you can call it a theorem if you'd rather not call it a corollary. And that is that for every k, there is an elliptic curve E over k with rank 0. In fact, with no non-trivial rational points at all. If k has a real embedding, then it's a corollary of this result, because this says that when r is 0, the number of twists of E with Selmer rank 0 is, there are lots of them. And so all of those curves have rank 0, and only finitely many of them can have any non-two torsion, and none of them have any two torsion. And this answers a question that was at least asked of us by Bjorn Poonen, but may have been around for a while. You wouldn't think this would be hard, and maybe in the end it's not, but it didn't seem to be known. And also, if you accept this conjecture that the two torsion in Shah has even dimension, then for every k there are elliptic curves over k with rank 1. Okay, so again, this isn't showing that a positive proportion of curves have rank 0 or 1 or anything else. We have some ideas for going in that direction, and I guess I'll get to those in a little bit. But let me first just give you some of the flavor of how we study this and how we prove this. And I also promised to define the Selmer group, so that's what I'm going to do now. Let me maybe do that over here. So the exact sequence I wrote I wrote down before with the rational points E of k mod 2 E of k mapping into the Selmer group actually begins its life as a map into the first cohomology group, H1 of the Galois group of K acting on the 2 torsion. And if you're not happy with Galois cohomology groups, think of this. So this is the same as just homomorphisms from the Galois group of K into the 2 torsion if the 2 torsion is all K rational. And if you're not familiar with the cohomology groups, then you might want to just stick to this case. Okay, well, for every completion of K, we can do the same thing. The local points, E of kv modulo twice E of kv, maps into the first cohomology group of the Galois group of the completion, kv, acting on the 2 torsion on E. This is called the Koomer map, and it's not really mysterious. All you do is you take a point here, you divide it by 2, and then you move it around by the Galois group. Well, the global points sit inside the points of the completion, just because K is contained in kv. And we can also take our cocycles, or our homomorphisms, and restrict from the Galois group of K to the decomposition group at V. So this map is called localization at V. And this map I'm going to call kappa sub V, or the Koomer map at V. And waving my hands, the Selmer group is going to live inside here. It's just going to be all the classes here, which in every localization live in the image of kappa V. So let me write that. So let H1F of kv E brackets 2, and you read this as a good subgroup of this group, and it's just going to be the image of kappa V. And then the Selmer group of E over K is the kernel of all the localization maps, which will take us from H1 of K E brackets 2 to the direct sum of all the H1 KV E brackets 2 mod H1F of KV E brackets 2. So it's all the cohomology classes, or all the homomorphisms, which, when restricted to the decomposition group, fall into the appropriate good subgroup. So again, think of it as we're looking at good cohomology classes, and good cohomology classes are determined by lots of local conditions. Anything that satisfies all the local conditions we call good, and we put it in the Selmer group. Okay, well, the point of going through this whole definition is to explain why families of quadratic twists are convenient for studying the variation in Selmer groups. And the reason is the following. What is the 2 torsion? After all, it's the set of points. Remember, our curve E was y squared equals f of x. So the 2 torsion is just the points where y is 0, and we take the roots of f. So we've got E1 0, E2 0, E3 0, and the origin, or the point at infinity, where f, so the f of x is just the product x minus ei, factored over the algebraic closure K bar. Well, what's the 2 torsion on EF? Well, remember, EF is just delta y squared equals f of x. And in that model, it's literally the same points. So we can identify these. And when we identify them, the way the Galois group permutes them is exactly the same. So these are the same. We have an isomorphism here as Galois modules. So in other words, H1 of K E brackets 2, or EF, the two torsion on the twist, we can identify with H1 of K E brackets 2. And the two Selmer group of the twist lives inside here, so we can think of it inside here. So for all these different F's, these Selmer groups all live in this same cohomology group, and all that's different are the local conditions that define them. So we're looking at cohomology classes satisfying certain local conditions. The local conditions vary, but the fact that we can look at them all in here is going to let us compare them. So let me say what I mean by that. So the easiest way to compare them is when we choose our F carefully so that only one of the local conditions changes. So let me just say, so suppose we have a prime P of the ring of integers of K, and I'm going to stay away from all the primes of bad reduction and any other finite set you like. And P is principal. It's principal. Even better with a generator pi. And to be safe, I could take pi to be congruent to 1 modulo 8 times the discriminant. Sometimes I do want to require something less, or things won't work, but this makes it safer. And totally positive. So positive at every real embedding. So this is some subset of positive density of all the primes of K. Any sorts of conditions like this give you a subset of positive density. But the statement is that if we let F be the quadratic extension K square root of pi, then the only condition that's going to change is the condition at pi. So then H1F of KV EF brackets 2 is equal to H1F KV E brackets 2 for all V different from this place, P. So we can compare, and we now want to compare the Selmer group of E and its twist, and there are going to be several cases. So case 1, that's going to be the case where E of K completed at pi has no two torsion. Okay, and so when does that happen? That's going to happen if this polynomial f, little f, has no roots in KV, or equivalently, so that'll happen if and only if the Frobenius of the prime P in the extension field of two torsion has order 3. Because this Galois group is a subgroup of GL2F2. It permutes the two torsion. If the element has order 3, then it doesn't fix any elements of two torsion, and that will translate into this. So again, this is something, since there is no two torsion, this extension is either cyclic of order 3 or S3. So there are elements of order 3, and so we know how often this happens. But when this does happen, you can check that well, actually, if you go back to this picture, E of kv has no 2 torsion, and E of kp has no 2 torsion. And p is different from 2, because we said pi was 1 mod 8. So in fact, E of kv is 2 divisible. And this quotient is 0. So for both E and its twist, h1f of kv ef brackets 2 h1 of kv e brackets 2. These are both 0. In particular, they're equal to each other. So not only are all the other local conditions the same, but even at p when we twist, the local conditions the same. So if you look at the definition of the Selmer group, nothing has changed. So it's the identical set of cohomology classes in the Selmer group for E and its twist. So the 2 Selmer group EF over K is just equal to the 2 Selmer group of E over K. And the ranks are equal. So in this case, nothing changes. And so this tells us if we have one twist of Selmer rank R, we get lots of them. This will give you an x over log x worth of such twists. And with a little more work, you get the stronger statement that I made. Okay. So that's maybe the least interesting case. So case 2 is going to be the case where if we complete at this chosen prime pi and we ask for the 2 torsion, this has order 2. So there's some 2 torsion, but not full 2 torsion locally. And in just the same way as I didn't really do over there, this is equivalent to saying that the Frobenius of P in the extension K join the 2 torsion. Has order 2. Because an element of order 2 in GL2F2 fixes a one-dimensional space. And again, we basically know how many elements there are. Of course, there may not be any if this was a cyclic group of order 3. But let me describe this case anyway. So if this does happen, then, well, then these H1Fs are, should have had an F, although it's true the other way too. These H1Fs are now different and one-dimensional. The dimension H1F KV is 1, and similarly for E upper F, and they're different. So something is going to change here. And what you can show, it depends on, so consider the localization map. We'll start in this Selmer group, E over K. And we're going to just localize at pi. That'll put us in H1F KV K pi E brackets 2. This is one-dimensional. And so there are 2 possibilities for the image. It's either 0-dimensional or 1-dimensional. And those 2 possibilities for the image are going to tell us what happens to the Selmer group. So, well, 2a, the dimension of the image of that localization map is 1. I want to say 1. 0 first. Then the Selmer rank of EF over K is going to be 1 more. plus 1. In case 2b, the dimension of the image is 1, then the Selmer rank is going to go down by 1. And what's more, I can tell you how often this happens. Among this set of primes, this is going to happen with probability 2 to the minus r, where r, I guess r is s. 2 to the minus s of e over k. If you think about it, here we have an s-dimensional vector space mapping into a 2-dimensional vector space. What's the probability if you just look at a random map that you get 0? Well, each of the s generators has to go to 0 out of these 2 elements. So that gives you a 2 to the minus s. And this is going to be 1 minus 2 to the minus s. So this we pretty well understand. And as long as you can choose primes like this, which you can't always, but you can sometimes, you can just repeatedly twist to decrease the rank by 1. And that'll give you a large chunk of the theorem I stated. Okay. So more interesting maybe, because we don't really understand it so well, is case 3, when e of k pi 2 torsion has order 4. And that's the remaining case. Order 4 means dimension 2. And again, that's if and only if, well, the last case, the Frobenius of P in K adjoin the 2 torsion over K is trivial, which certainly can happen. Now we still look at this localization map, but now there are 3 possibilities, because the dimension of the image can be 0, 1, or 2. So 3. Let me do it over here. So 3a, the dimension of the image of localization well, it's 0. I'm going to save that case for last, in fact. 3b, the dimension is 1. 3c, the dimension is 2. In this case, the Selmer rank is going to go down by 2. In this case, it's not going to change. I mean, the Selmer group itself will change, but the rank won't. And in this case, unfortunately, there are 2 possibilities. And that is that the Selmer group might go up by 2, and it might not change. And I can tell you how often these 3 cases happen. Again, this one, well, what's the chance that this map is actually 0? Well, now it's 4 to the minus s. So these 2 cases together have probability of happening 4 to the minus s. What's the chance that the image is 2-dimensional? Well, there are 3 lines. And so the chance that it's hitting exactly one of those lines is 3 times 2 to the minus s minus 4 to the minus s. And the other case is the rest. So this is kind of everything we want to know, except how this case divides up. And we don't understand that so well. So the guess, and it's confirmed by numerical calculations, is that these two subcases happen equally often. And one reason that's nice, if that's what happens, is that then the different probabilities in case 3 match up exactly with the probabilities in case 2 if you do it twice. After all, if you do this twice, you're either going to go up by 2 or down by 2 or be unchanged. And you can easily figure out what the probabilities are. And that'll match exactly with these if these two are split in half. OK, so what is it that we're doing here? Well, we're trying to view this as a Markov process, where you start with something of rank r, you throw another prime into your twist, and you either go up or go down or don't change with certain probabilities, and you see what happens in the limit. And so if you view this as a Markov process and you believe this guess, and you ignore the fact that we're not really looking at all primes, because I put some conditions on them at the beginning, the equilibrium state for this, the limiting state for this process, is exactly the distribution of C sub r's. OK, so I'll just say that the C sub r's are the limiting distribution for this Markov process. And if you think of things this way, it also tells you why Selmer ranks tend to be small. After all, the probability that's going to go up is much less than the probability that's going to go down. And the higher it is, the more likely it is to go down rather than up. And that leads to these values C sub r that fall off very quickly. OK, well, let me finish with one sort of just a very special case of this question here that leads to a question that has nothing to do with elliptic curves, just a question about algebraic number fields. So my example, so I'm going to take E to be the elliptic curve y squared equals x cubed minus 7x minus 7. And this is 784 G1 in Cremona's tables. So the conductor is 2 to the 4th times 7 squared. What's interesting for us is that, first of all, the Selmer rank is 0. So there's no 2 torsion. The rank is 0. The field of 2 torsion, well, in fact, is ramified only at 7, and it's a cyclic cubic extension. So it's the real subfield of the field of 7th roots of unity. What else do I want to say? So, by the way, we're in. So if P is, if our rational prime P is congruent to 1 mod 7, or plus or minus 1 mod 7, then it splits in this field. And so that means we're in this case, well, we're in case 3, because the Frobenius in this cubic extension is trivial. And in fact, we have to be in case 3a, because the Selmer group is trivial, so the image when we localize is 0. So we're in this case, and we just want to know, does the Selmer rank stay the same, stay 0, or does it go up by 2? Up 2, 2. Then case 3a. And what we can say is the following. So let's take our prime here. It splits in this cubic field, so P factors as P1, P2, P3. This field has class number 1, and what's more, it has it's totally real, and it has units of every possible sign pattern. And so that means each PI has a totally positive generator. You just multiply it by the appropriate unit. Call it pi I. And that generator, because there's only one choice of unit to make it totally positive, it's unique up to squares. So pi I is unique up to the square of a unit. So let me make a slight extra hypothesis. So suppose that this pi I is also congruent to 1 mod 4. And it doesn't matter which I you choose, they'll all be equivalent. And so this amounts to asking not just that P splits in this cubic field, but it splits in a certain ray class field of this cubic field. But let me just suppose that. And then I can tell you which of these two cases we're in. Then the Selmer rank of E twisted by P over Q is 2 if pi I is congruent to a square mod pi j, and it doesn't depend on which I and j you pick as long as they're different. And it's 0 otherwise, if not. Now, experimentally, this happens half the time. It's not hard to check that. But we don't know why that is. So my question is, just looking at this statement, you look at primes congruent to plus or minus 1 mod 7, where the prime above it, where your generator, actually, since this is unique up to square, I guess we can say just pi is congruent to a square mod 4 would be fine here. That makes it better defined. Well, mod 4. This seems to happen half the time. So why? I mean, the obvious answer is that there should be some Chebytarov condition, some condition that says if your prime splits in a certain way or has a certain Frobenius in some extension of L, then that puts you in one of these cases instead of the other. But we've been unable to find such a condition. So is there some Chebytarov condition that explains it? And so in particular, this would depend on choosing some extension of L, say, for some field M containing L, Galois over Q. And we can do experiments that rule out lots of obvious guesses for what M could be. For example, if M is abelian over L, then it has to be ramified at some prime different from 2 or 7 or infinity. And why should that be? There are no other primes that play any role in this picture. Other obvious fields like the 8 torsion on the elliptic curve or something like that, I mean, you can just check that they don't work. Those fields do not separate the primes in these two cases. On the other hand, if there's no Chebytarov condition, it's hard to imagine how you could prove such a thing. I mean, how do you prove anything about a density of primes without such a condition? If you can generalize this question quite easily. It doesn't have to have a cubic field here. If you want a little exercise, try it with a quadratic field. And there you can show that a quadratic reciprocity will show you a Chebytarov condition that tells you when pi bar is a square mod pi. But as soon as you get to this cubic case, it seems very mysterious. So thank you for your attention. And if you can answer the question, please let us know. Yeah.
You say that the ramp is more likely to go down than up, but occasionally it still goes up.
Yes.
Can you use it to show that it's unbounded?
No. Well, you can use it to show that the Selmer rank is unbounded.
Sure, of course.
Yes.
Yeah, still,
Oh, yes.
you can deliberately construct a sequence.
Yes. Yeah. I mean, I mean, it wouldn't be very efficient if you wanted to do it numerically. But at each stage, I could give you sort of, I mean, effectively, congruence conditions on the next prime to guarantee that the Selmer. I mean, and we can't do that for all curves, but we could do that for example, curves with curves over Q with negative discriminant, and no two-torsion, no rational two-torsion. Yes. But I think you wouldn't want to do it in practice. I mean, the numbers would be horrendous.
In practice, you know it's unbounded.
Yeah. Yeah.
Would there be, for every number field, an elliptic curve over Q having rank 0 just number fields?
So actually, I mean, I didn't go into it, but this work was motivated by a different question of Bjorn Poonen that had applications to Hilbert's 10th problem. And the idea there was to show that if you had a cyclic extension of degree p of number fields, you could find a curve that had rank 1 at the bottom and still had rank 1 at the top. So again, we can prove that for any cyclic extension of degree p, you can find an elliptic curve over Q of rank 0 that has rank 0 up top. But I wouldn't know how to do that for any field, but it's undoubtedly true, so there might be some hope.
Any other questions? Let's speak over.